Today we'll be working on the following problem. Let's construct a real function f, which is Lebesgue measurable, such that for any z subset of R1 with the Lebesgue measure 0, f of x is not continuous on any of x in the complement of z. Pause the video if you want to work on this problem by yourself. Okay, let's see how we find such a function f. Solution. First, let's see what is the motivation for this problem. And we want to improve the losing theorem. So losing theorem says like losing theorem basically says for any delta greater than 0, we can find some closed set f in R1 such that the measure of the complement of R of f is less than delta, this given delta, and f of x is continuous on f. That is the losing theorem, right? So basically we want to say like, okay, can this delta be 0? So if delta is 0, which means like we can find a, which 0 0 measure set z, this become our z, right? So f of x is continuous on the complement of z, right? So now we're going to see like, okay, the losing theorem, the conclusion cannot be improved because of the example we're going to present. So let's first look at some of the well-known functions. For example, like, first like the Dirichlet function. The Dirichlet function defined to be, if x is any rational number, is 1. X is not rational number, it defined to be 0. So we know this function is nowhere continuous on R, right? However, this is not what we want. This function does not have the property we want, because when we remove this rational number, which has the measure 0, right? The big measure 0. So d of x actually is continuous on R minus Q, right? So when we remove this 0 measure set, then R become a constant 0. So of course it's continuous. So that's not what we want. So for example, another one, we can look at the Riemann function, which defined to be like this, right? So if q 1 over q, if x is in the form of p over q, which is rational, so we define the value to be 1 over q. So if x is irrational, we define to be 0, right? So this function, we know it is a discontinuous at every rational numbers. But it's discontinuous on Q. So this is also not what we want, right? Because then we just remove this rational numbers, and then the rest become what? all irrational constant. So again, this is continuous on R minus Q, right? So, and also we know actually any monotonic function, any monotonic function has a discontinuous at the most countable point, right? Discontinuous at the most countable points. So hence, when we remove this countable points, which has the bigger measure 0, then this monotonic function is continuous everywhere, right? So those are some of the functions that it does not have the property we want. So if we recall, okay, I'll recall the from last problem, we can find E and F in R. They are disjoint, right? And then for all open interval, open segment I non-empty, we have this. The measure of E intersect I is greater than 0, and then also this F intersect I is also greater than 0, right? So from this we define, from this we can define our function. Define F to be the characteristic function of one of them. Let's see, of E. So which means f of x equals 1 if x is in E. Otherwise is 0. So let's check this function is what we want. Meaning like for any z with the bigger measure 0. If we look at this set, we know this the x is in this and any open interval and the open segment, for any open segment I which contains some fixed x0 in this R over minus z, right? So remove this z and then we pick any x sub 0. So we want to show like f of x is not continuous at this point. So we pick any open set I contains this x sub 0 for any, and this so if we look at this x in the interval minus z for f of x equal to 0, this set is the same as this set, right? Because f of x is either 1 or 0 depending on whether it is in E or not. So this is actually the same as like x in is the set of E intersect I and then minus z, right? These two sets are the same. And then if we take at the and then we take the Lebesgue measure of this. Is the Lebesgue measure of this, and because z is has a Lebesgue measure 0, so it doesn't matter. This will be the same as E intersect I, which is greater than 0, right? So if we look at similarly, we look at the same like x in I minus this z, but f of x is equal to 0. This set is actually contains the set of f intersect I and then minus z, right? Because for any point in f, which is not in E, because E and F are disjoint, if it's not in E, this becomes 0. So, and then the measure of this is greater than or equal to the measure of this, and then again, Z has measure 0, so it does not impact the measure of F over Z greater than 0. So what do we have for any open interval I contains x sub 0, picking any fixed x sub 0. So the set of we have the set of is 1 has a measure positive measure, and also has when the measure when the f of for which f of x 0 also have a positive measure. So there are infinitely many x for which f of x is 1, and then another infinitely many f of x is 0. So f of x is not continuous at x equal to x sub 0, right? It cannot be continuous. So they have either infinitely many 1 and 0. So this is this f is what we want, has all the properties we expect to see, right? That's it.